I want to dye, and to do that I need the perfect dye. After completing 5 organic syntheses, starting with toluene and ending with sulfanilic acid, we are finally ready to create a vibrant dye. Today we'll use the previously produced sulfanilic acid to synthesize methyl orange, one of the most striking azo dyes. Let's dive into the colorful world of chemistry. Azo dyes are a significant class of synthetic dyes, characterized by one or more azo groups, which forms part of the chromophore that gives these compounds their vivid colors. Due to their intense colors and relatively straightforward synthesis, these dyes are widely used in various industries, including textile, leather, food, and cosmetics. One of the most well-known azo dyes is methyl orange. Methyl orange is an organic compound that belongs to the azo dye family. As you know, this means it contains an azo group. The dye is frequently used as a pH indicator in titrations due to its straightforward and distinct color changes between acidic and basic environments. Its vibrant color changes as it's red in acidic solutions and yellow in basic solutions. This sharp color transition makes methyl orange particularly useful in analytical chemistry. Beyond its role as an indicator, methyl orange is widely used and advantageous in textile dyeing processes because of its bright colors. In textile industries, methyl orange can dye fabrics and fibers, providing vibrant and long-lasting hues. Despite its efficacy, the use of azo dyes, including methyl orange, has raised environmental concerns due to their potential toxicity and persistence in water bodies. As a result, the management of azo dye effluents has become an urgent and important focus in environmental chemistry, highlighting the need for immediate action. While azo dyes are widely appreciated for their vibrant colors, they come with significant toxicity concerns. These dyes can break down into aromatic amines, compounds that are often toxic and mutagenic or carcinogenic. When ingested or metabolized, the azo bond can cleave, releasing harmful substances such as benzene, known for its carcinogenic properties. Moreover, azo dyes are persistent in the environment, leading to potential long-term ecological damage. The potential health risks associated with azo dyes, especially when used in food products, are a cause for concern and require careful regulation and monitoring. Due to their potential health hazards, their use is regulated and safer alternatives are continually being researched and developed, except here in the United States, where our food industry is in shambles. Ever heard of red dye 40? You guessed it, it's an azo dye. Yellow 5? Another azo dye. While some azo dyes are known toxic and agreed upon, like methyl orange, there aren't a consensus on many common dyes used in our food. Just a lot of European countries banning it for no good reason, making it hard to dye our food bright and yummy colors. The structure of methyl orange consists of a benzene ring with an amine, linked by an azo group, which is then connected to a secondary aromatic ring containing a sulfonate group. This sulfonate group enhances the dye's solubility in water, making it more practical for various applications. The presence of an azo linkage is critical as it imparts the characteristic color to the dye. So now, how do we make this linkage? A list of all the needed equipment and chemicals can be found in the description. The first step that we need to complete is diazotization of our sulfanilic acid. Diazotization is a chemical process used to convert an aromatic amine to a diazonium salt, which is essential in synthesizing azo dyes and other organic compounds. To start, we prepare a beaker of sodium sulfonate solution by placing 20 milliliters of a 5% sodium carbonate solution in a 600 milliliter beaker, and then diluting it with 30 milliliters of water to bring the total to 50 milliliters. Next, we add 0.03 moles, 5.2 grams of anhydrous sulfanilic acid, or 5.8 grams of the hydrate to this mix. It is then warmed slightly on a hot plate to aid in dissolving the sulfanilic acid. The acid did not dissolve completely, so I added a little bit more of the 5% sodium carbonate solution, 5 to 6 milliliters. We need to ensure that it does not exceed 6 milliliters, as adding too much solution will add too much base, which will prevent the next step from occurring. I then threw in a stir bar to help agitate the solution and help it dissolve faster. Depending on its purity, it may not all dissolve. So if that does happen, the solution needs to be filtered and to remove any of the undissolved solids. Due to our due diligence in the last synthesis, we have very pure sulfanilic acid. So this was not a problem for us, and we can proceed to the next step. Next, we weigh out 0.05 moles, 1.8 grams of sodium nitrite. We then dissolve this in about 10 milliliters of water, and add this nitrite solution to the sodium sulfonate solution. We then cool the mixture in an ice water bath until the temperature reaches between 0 and 5 degrees Celsius. We continue to stir the solution vigorously and add a mixture of 3 milliliters concentrated hydrochloric acid diluted with 5 milliliters of water drop by drop. The reaction is exothermic and produces heat, so we must add the hydrochloric acid slowly so too much heat is not generated. The hydrochloric acid reacts with the sodium nitrate to produce nitrous acid. This nitrous acid causes diazotization, forming the diazonium salt. It is crucial to proceed immediately to the next step, as the resulting diazonium solution is unstable and should be not left standing longer than necessary. The next step is a coupling step where we take the diazonium sodium salt that we just produced and couple it with an aromatic ring. Next, into a 25 milliliter Erlenmeyer flask, we add 0.025 moles, 3 grams of diethylaniline, followed by 0.027 moles, 1.5 grams of glacial acetic acid. Then we mix thoroughly. Next, we quickly add the diethylaniline acetate we just made with the diazonium sodium salt solution while stirring vigorously, and allow the mixture to stand and react for around 5 to 10 minutes. The nucleophilic aromatic ring of the diethylaniline attacks the electrophilic diazonium group, resulting in the formation of an azo bond. This coupling produces our dye, methyl orange. Finally, we make the solution strongly alkaline by adding a solution of 3.5 grams of solid sodium hydroxide in 10 milliliters of water. This addition causes the deep red color to change to a yellowish orange. The methyl orange precipitates as well. We can make it precipitate more completely by adding 10 grams of clean salt. We then collect the precipitate with suction using a Buchner funnel and filter paper, and using a bit of ice-cold water to wash out the beaker into the funnel. After filtering for a while, we are left with a nice orange mass. Right now, our methyl orange has impurities in the form of unreacted compounds, sodium hydroxide, and other junk. To get rid of this, we need to do a recrystallization. Using boiling water, we add it to a beaker containing our crude methyl orange, keeping it warm on a hot plate. It takes around 10 to 12 milliliters of hot water per gram of material. We want to add enough to dissolve all the methyl orange, but not too much that we lose product by leaving it dissolved while filtering. We then set the beaker off to the side to cool. The methyl orange is pretty insoluble in cold water and starts to crystallize out. Once cool, I transfer it to a glass fritted filter to remove any liquid, using some cold ethanol to aid in the transfer. The ethanol was also washed through the methyl orange a few times. After the ethanol washes, diethyl ether is passed through till it runs clear. I left the pump running for a while to pull air through to dry the orange dye completely. Now with our purified methyl orange, it was transferred to a tared vial. The yield was just shy of 4 grams of methyl orange. We lost a lot of the dye due to it getting stuck in various places to the glassware. Also, my sodium nitrite is quite old, which most likely led to poor yields. I can see a lot of the aniline did not react. So this is the part of the video where I normally do some analytical methods to show what I made is what I said I did. But it's an orange powder, and I can prove that it's orange. Using a device known as a UV vis, we can look at the wavelengths the compound absorbs at and tell a lot of information about the compound. We start by filling a cuvette, the square test tube thing, with water, then insert it into the instrument and blank it. This is so the instrument ignores the absorbance of the water molecules. Next, we dissolve a bit of the methyl orange into the water and reinsert the cuvette into the instrument. Then we measure the absorbance. From this, we can tell it's orange because the absorbance is in the range of 200 to 620 nanometers. The gap in the visible light spectrum absorbance corresponds to the range of orange. We see color by seeing its reflection. What we're looking at isn't actually the color we see, just the kind of light that it's reflecting. To test the indicator properties of the methyl orange we made, I dissolved some methyl orange into 3 vials of water. Next, to one of the vials, I add some acid. This turns the methyl orange dark red. To another, I added some sodium hydroxide, and this turns the methyl orange a yellowish color. In the middle, we see our normal orange color that we got from just dissolving it in a neutral solution. In the acidic conditions, methyl orange exists in a protonated form, where the nitrogen of the azo group is protonated, resulting in a more positive charge. This form of methyl orange appears red due to the extended conjugated of the double bonds. In the neutral conditions, methyl orange is partially protonated state, leading to its orange color, while in the solution of alkaline, the methyl orange is deprotonated, and the structure shifts to an anionic form. This form has a different conjugated pattern, resulting in the yellow color. Thanks for watching.